Hello everyone. Today I will talk about shortest unique substring queries. This is a joint work by me, Oğuzhan Külekçi, and Bojin Shu. Outline of my talk is, first I will define the problem, of course, and give the preliminary information about the data structures we used in our algorithm. Then I will explain the cornerstone of our algorithms, which is left-bounded shortest unique substrings. After that, I will explain one of our 4 algorithms, which is finding the shortest unique substring for every position in the string, and the experimental results compared with the other algorithms which do the same work, conclusions, acknowledgements, and questions. First, a little bit of history. It's actually very little, because the problem proposed by P and the co-authors in their 2013 ICDE paper. The problem is finding for every position in the string, essentially we are trying to find the substring which is the shortest and also does not appear anywhere else in the string. We considered 4 problems related to the shortest unique substrings. First one, we are taking the text as well as a position as an input and finding the leftmost shortest unique substring covering that particular position. Second one is finding all shortest unique substrings, because there can be multiple. Third problem is its generalization over a whole string, finding all unique leftmost shortest unique substring for all positions. And the fourth one is, again, its generalization, finding all shortest unique substrings. Why we are doing this? Shortest unique substrings can be used by distinguishing the results in a text search. For example, you searched a word in a long text and you have to distinguish its appearances. So one way of doing it, that's giving the snippets of the text which contains the word which is searched. But giving a fixed length maybe can cause to the same snippets, because the context will be similar where the word is used if it's not a generic word. Or if you give too long snippets, it will be hard for a user to distinguish them apart. Also, we can find DNA signatures of organisms. DNA signatures are the portions of the DNA where one organism of the species distinguished from the other one, like differentiates me and everybody else in this room. Also, extracting the event context in historical events. For the series of the similar historical events, we can extract what makes the particular event unique and different from the other events in the history. Okay, let's go to the preliminary data structures. These are the very well-known data structures, suffix array and rank array. I'm sure everybody in here knows that, but I will tell them for the sake of simplicity. We take all the suffixes of the firstly, the suffix array is a position of a given suffix in the lexicographically sorted order in all suffixes of the string, and the rank array, or also known as inverse suffix array, is the position in the order. How can we do that? We take all the suffixes. It's the most basic way of doing it, sorting them in the order and taking their beginning position as the suffix array, and the construction of the rank array is trivial once you have the suffix array. Other data structure we will use is longest common prefix array. Longest common prefix array contains the length of the longest common prefix between suffix I and I minus suffix I and I minus 1. Because of the first suffix because of the first suffix has no predecessor, the longest common prefix array will be defined as 0 for that. This is, again, a well-known data structure, so no dwelling on it. What is left-bounded? Shortest substring, unique substrings. These are defined for every position on the text. They are basically the unique shortest possible unique substrings beginning from that particular position, k, given k. So here are some examples for the string Mississippi. M is the Alsace 1 for the first position. The ISIS is the Alsace 2 for second position. We are skipping the middle parts. PI for the Alsace 1 for the 10th position, which is P. And sometimes some Alsace may not be exist because the remaining suffix may repeat in the string. We can determine constant time these Alsace from the LCP array and the rank array. The main observation in here is that we have to compare the suffix I with the suffix the predecessor and the successor suffixes in the sorted order, because it has to be the longest common portion between one of them. So extending that longest common portion will give us a unique substring which does not appear anywhere in the string. So this, and if the boundary of that extension goes over to the boundary of the string, we can say that then that suffix is actually a repeat and the Alsace I not exist. So we are looking the position where the comparison of the suffix I with the I minus 1, which is the rank I in the LCP array, and also comparison with the suffix I with the or I plus 1 in the sorted order with the rank next position in the LCP array. So let's look at the example construction. We go to the position 1 in the rank array. It says that the suffix 1 is in the 5th position in the sorted order. We go to position 5 and the 6. We take maximum of them, which is 0. So it's from position I to position I, which is the singleton M. Next, we go to the rank 2. It says that the suffix 2 is in the 4th position. We take the 4 and 5 of the LCP array. The maximum is 4. Therefore, we need to take the substring from 2 to 6, which is this. Next one, we have to go to position 11. Position 11 doesn't have any successor in the LCP array, so we are taking this value only. And we have to take from 3 to 6 as the Alsace. I'm again skipping the steps. For Alsace 9, we go to the rank 9, and it says the LCP 7 and 8, so 1 and the PP. For Alsace 10, we go to the LCP 6, it's 6 and 7, it's 1 PI. For Alsace 11, we go to the position 1, it's 0 and 1, we take 1. Now we have to take Alsaces from string 11 and the 12th position, but the string's length is 11. Therefore, Alsace 11 does not exist. There are two important properties of the Alsace which helped us construct our algorithm. First one, we always know that the Alsace 1 always exists, because in the worst case, the string itself is unique. Therefore, Alsace 1 can be the string itself. Second, more important one, is that Alsace I cannot end before Alsace I minus 1, if they are both existing, of course. Let's say that that black line represents our Alsace 1. It's ended in the character A, so Alsace 2 beginning from character B ends in character D or before that, we know that from the definition of the LSAS, it should be a repeat. Therefore, it cannot be an LSAS. So it should end at least the position A. Okay, for our algorithm, it depends on the fact that every shortest unique substring is either itself an LSAS or the right extension of an LSAS. We need to determine the case where which is which with this condition. We are using it. First, SLS, shortest left-bounded substring I, leftmost shortest LSAS covering a position I. It's another definition. Let's look at the condition now. We can take the shortest unique substring covering position I-1, extend it by one character, which gives another unique substring also covering position I. It's a candidate. Also, the SLSI is the candidate. So the extension cases will be covered by this option, and the LSAS case itself covered by this option. We are just comparing the lengths of them, taking the shortest one, and if there is an equality, because we are returning the leftmost, we will choose the extension, because it should be the leftmost one. Now we have a problem of keeping those SLS I candidates and retrieving them when we are calculating the LSAS I. What we do is we have chunks, non-overlapping chunks of the positions, which we will record the candidates for these positions. These candidates will be the LSASs, where the shortest ones covering that. Let's look at this example. That black line is our LSAS 1. And the candidates will be updated either if they have no candidate or the new LSAS is shorter than their candidate. So none of these positions have candidates before, so we are creating a new chunk from position 1 to 4 and record the LSAS 1 as their candidate. Let's go to the LSAS 2. Our LSAS 2 is this one. These have the candidates of 4, but the B and C doesn't have any candidates for itself. So we are creating a new chunk for B and C, and its SLS candidate will be the LSAS 2. We get rid of the position A because when we use the SLS A, we will calculate the SLS 1. We will calculate the SAS 1, so we don't need to record it anymore. Let's go to the 3. We again get rid of the candidate of B. We have a new LSAS 3, which is length 4. Candidate of the blue chunk have a length 5. So we have a shorter LSAS, so a better candidate for the positions in the chunk blue. Its candidate is changed. I represented it with color change in here. So the candidates for positions, this B and C, will be the LSAS 3 now. Let's go over LSAS 4. Again, this is length 4. These are not changing because they are not smaller, and we record a new candidate for the B. And LSAS 5 has length 3. Now we get rid of the A, so only 2 chunks left, and the 3 is shorter for all of their candidates, which was 4. So we discarded these chunks and create a new chunk containing all the positions BCB as a candidate of LSAS 5. How we are recording these chunks and these candidates, we are using a double linked list, basically. It has a pointers from previous and next nodes. Chunk start, chunk end, LSAS start, and LSAS length fields. Chunks, let's look at the second black chunk in here, which is AC, because it's non-trivial. So chunk start for this chunk will be the 4 position of the A. Chunk end will be the phi position of the C. Elsa's start will be the 2, because the green one is the Elsa's of this one. And the Elsa's length will be the 4 of the length of the Elsa's. Now, the example run of our algorithm for better understanding, we start with the string, Mississippi again. We have an empty list of the candidates. At first, we calculate the Elsa's 1 from the LCP and rank array. It's M, so we create a new node with the chunk. It's starting from position 1, ending in position 1. Its candidate starts from position 1 and has length 1. No previous shortest unique substring. We have candidate 1, 1. Therefore, our shortest unique substring will be the 1, 1. Let's go to the next iteration. Again, we calculated the Elsa's 2. Now we discarded the position 1. Therefore, we removed that node at the beginning of the second step. We create a new node where from position 2 to 6, which records the Elsa's 2 as with the starting 2 and the length of 5. The previous shortest unique substring has length 1. Our new candidate has length 5. So we added the 1 compared to with the 5. So the shortest one will be extending the previous shortest unique substring. Third iteration, again, we calculated the Elsa's. Because it's shorter, it's a better candidate, so we have to discard the previous node and create a new node with the new candidate. We then read the SLS3. Elsa's 2 was 1, 2, SLS3 is 3, 4. So increasing the Elsa's 2's length by 1 gives us a shorter substring, therefore we are choosing it. Going to the next one. Now we have the equal lengths now, but we have to extend this one by 1, so choosing this Elsa's as the shortest unique substring gives us a shorter one. Now we have length 5 Elsa's, which is longer than the candidates of position 5 and 6. So we have to create a new node added to the end of our list, which will record the candidates for position 7, 8, and 9, which is beginning from 5 and has length of 5. Then we are again looking at the head node, we will always look at the head node, taking the candidate from that node, 4, 3, previous one, the 4, 3. So increasing this by 1 will give us a longer substring. Therefore, we are choosing the candidate again. It's the same thing. We again decreased this one, calculated. Because it has the longer length, we recorded the position from 7 to 9 as the new Elsa's as our candidate. Again, we are reading the candidate from head node and comparing and finding. Because our head node now is depleted, we discarded it. We only have the one node left. We calculated Elsa's again. We revised it because it is shorter, acquired, and make the comparison. Goes on same. They are doing the same thing over and over again. If we don't have any candidate, we don't have make any changes on the data structure. We just retrieve what we have on the data structure as a candidate and make comparison again. Let's get to the complexity of our algorithm. I think I have 5 minutes, okay. Derivation of the LCP and the rank array can be done in linear time. The references can be found in the proceedings. They are borrowed from other works. Calculation of the Elsa's takes constant time for each position. maintenance of the data structure, this is amortized constant time because there's a revision operation which goes backwards on the list and the merging to all the, discarding all the candidates which have the longer candidate from our current LSAS. But at every step, we only inserting one node to this list, and also we have no splitting operation. Therefore, there can be only linear number of nodes can be removed by the revision operation, which brings us an amortized constant time for each data structure operation. Finding the candidate is just looking at the head node, so it's constant time. Determining sus is just integer comparison. We have to do it n times. So in the total, it will be linear time. Space complexity, we have LCP array, linear in the number of positions in string for words. Rank array, and the data structure, again, because the size of every node is constant and it has at most n nodes in the data structure, it will take a linear space. And we have to hold the previous sus, which is constant. So it has the constant time. When we completed our work and write the first draft and put it on the archive, writers of this second paper contacted us and informed about their work, which was submitted, accepted but not published that time. So also, they were kind to provide their implementation to us to make the experimental work and compare our algorithm. This is the original work, which gives the it stated the problem and they give the initial solution. So all the implementations are coded in C++, run on the same machine. We used Pizza and Chili corpus data for our testing. We take the 50, 100, and 200 megabytes of the English text, DNA text, and DBLP text in the Pizza Chili corpus. This one is the initial work of the Pei et al. The second one is the work of the Tsutara et al. And the third one is our work. Because the initial work has the time complexity quadratic in the input size, it just blows up at some point. We are 1.2 times slower than the Tsutara's work for almost all the cases. It depends on it changes over the 1.2, 1.4. We couldn't run the initial code for more than 50 megabytes because it uses a lot of space and the memory in our computers doesn't have enough to do it. This is time measurements. Here are memory measurements. Again, this is the initial work. This is our work, and this is the Tsutara's work. So we are approximately 4 times efficient in terms of memory for the Tsutara et al.'s work. So it gives a kind of trade-off between speed, time, and memory. It's because theoretically they all use the linear time and linear memory. In conclusion, we developed a linear time and space algorithm for finding sus covering 1 positions and all positions. Our work improved the prior work, which is initial work, 8 times in terms of time and 20 times in terms of memory. The huge memory improvement comes from the fact that the initial work used the suffix trees and we are using the suffix arrays, so which is much more memory efficient. I want to thank you, the CPM organizing committee and the Bilim Akademisi Foundation in Turkey for their monetary support so I can attend the conference. And thank you for listening.
Are there any questions? No questions. So I have one quick question. So let's say that your text is growing, so you're appending new letters. Can you update the data structure, which allows you to later find the shortest unique substring?
You are asking about the online, I guess. If you have to somehow calculate the LCP and the rank array online, if you can do it, algorithm can find it. Yeah, it's adaptable. It always goes over iterated from one point.
Okay, thank you. So let's thank the speaker again.